Hello, I welcome you to this very important class where we're going to be looking at Laplace transform. This is more or less an introductory class to the topic Laplace transform. A prerequisite for this class is that by now you should have been conversant with integration. Now, basically, integration of exponential functions. When you have an exponent, how is the integration done? So I would advise that you refer back to your engineering mathematics and study how to carry out the integration of an exponential function. Having understood that, it's also important that you know basic differential equations, although we may not delve too much into that, but just have a basic knowledge of differential equation, first order, second order. You should be able to identify a first order or a second order, or perhaps even a third order differential equation. Then, having done that, good. You are ready for this class. Now in this class, we are going to be looking at the definition of Laplace transform. We're also going to be looking at solving a few problems using the Laplace transform or finding the Laplace transform of a few functions. We're also going to be looking at the Laplace transform properties. Then we'll also consider the table of Laplace transform pairs. It's going to be, I believe, a very interesting class. Just take your time, arm yourself with your writing parts, listing as much as possible, take notes where you consider necessary. Now let's move into the class proper. What is Laplace transform? Laplace transform is an integral transformation of a function f of t from time domain into the complex frequency domain, given as f of x. Given a function f of t is Laplace transform, which we have as a symbol L here. This symbol here represents Laplace transform. The Laplace transform of a function in time domain, which produces a function also what? In frequency domain. Now we can express Laplace transform mathematically in this form. The Laplace transform of f of t, which is equal to what? F of x in frequency domain is equal to that, an integral that integrates the function f of t from 0 to what? Minus infinity over the exponent minus s of t dt. So this is the formula for what? The Laplace transform. So if you are asked to mathematically state, or you wish to state the Laplace transform definition mathematically, this is the definition you are expected to give. Now, you are also expected to explain this, where s is what? A complex variable given by what? X is equal to a plus j omega. This x here is a complex variable, complex frequency variable. Now is given to us as what? A plus j omega, where a is the real part of the frequency and omega is the imaginary part of the frequency. Now, the Laplace transform can be represented as unilateral or bilateral. That is one-sided or what? Two-sided. Now, in some textbooks, you will see them express Laplace transform in this form. When you see it in this form, what they mean is actually the two-sided Laplace transformation, which is an integration from minus infinity to what? Infinity. The one-sided is an integration from 0 to infinity. Recall that this actually means minus infinity to 0, then from 0 to infinity. That is two-sided. Now from minus infinity, then you stop at 0, then from 0 also to what? Infinity. So you see you have double side, and that's why it's called two-sided Laplace transform. Now the existence of the Laplace transform. The Laplace transform f of t of the Laplace function f of x of a function f of t exists if the integral or the Laplace transform of that function is less than infinity. Also, another important thing worth noting, you can also find in some books when you read, is if the function is integrable. If the function cannot be integrated, then its Laplace transform does not exist, because Laplace transform is an integral transform, which is to say it's going to integrate the function, moving it from what? A time domain to what? A frequency domain. So let's look at some examples here. let's consider some examples of Laplace transform. Well, we are going to start with some function. Well, I do not know. They may be common to you, they may not, but they are very important functions in mathematics. Here we are asked to determine the Laplace transform of the following functions. We have a, u of t, b, an exponential function, raised to power minus a of t. Then we have c, an impulse function. Then D will have a sine function. Now, if we have all of these functions and we're asked to look for their Laplace transform, let's start with u of t. Here we have the Laplace transform of u of t. What is the Laplace transform of u of t? That's now this u, its magnitude here is 1. It's actually a unit step function. It has a magnitude of what? Unity. So here we're representing it with its magnitude. Now, when you see a function attached with this u of t, now in carrying out the integration of this function or the Laplace transform of this function, you're going to integrate it from 0 to what? Infinity. Once you see this u of t attached, what we are looking at here is that this is going to be a one-sided what? Laplace transform that we are to integrate from 0 to what? Minus what? From 0 to what? Infinity. And the magnitude for this function is actually what? 1. Yes, its magnitude is 1. So that's why we are using 1 here. So we integrate this. So invariably, you're going to have 1 times this. So what we're going to be integrating invariably is just this function. Now, like I told you, if you know the way to integrate an exponential function, so we carry out the integration, you're going to have this minus 1 over x exponential minus s of t. Now, our limit of integration is from 0 to what? Infinity. That is the limit of integration we're considering from 0 to what? Infinity, and this will be equal to this. Now you have this. We're going to now substitute this 0 and infinity for t. So whenever we see t, we substitute what? 0 and infinity. So when we put this 0, when we put start with what? Infinity, you know we are going to have minus that, minus 1 over x. Now infinity, when infinity multiplies this, everything here will become 0, because what we are going to be having here will look like, you remember that this minus s of t is the same thing. You can say 1 all over e raised to power minus st. I mean 1 all over e raised to power st. That's what this thing means. So go and evaluate that. You're going to find out that everything here will be 0 when you substitute minus infinity. Will be 0. Then you know it's going to be the upper limit minus the lower limit. That is 1 all over x, imputing the infinity, then minus, because mind you that you are going to have subtracting the lower boundary, which is 0, then minus, then you're going to impute 0 here. When you impute 0 here, of course, you know this function, anything raised to power 0 is going to be 1. Because if you still recall your mathematics very well, this is going to be like exponent here. This is going to be 1 all over, like we said, 1 all over exponent st. So if t is 0, it's going to be 1 all over exponent 0 is 1, which is going to be 1 all over 1. And that's why you're going to have 1 here. Mind you, this 1 over s is multiplying everything inside here, because we're considering minus, infinity minus 0. So you're going to have 1 over x, and that is 1. And when you do your arithmetics here, this side becomes 0. You're going to be left with 1 over x. So this is one way out. Now we consider the second part of it, the b part, which is exponential minus 80. Now, when you have exponential minus 80, remember what we told you about this. This is telling you that this is a function, is a one-sided Laplace transform. We are to integrate from 0 to what? Infinity. So you have here exponential minus a of t. So the magnitude here is exponential a of t, and that's why we're using exponential a of t. Whereas here we use 1. Remember, do not forget. Then this is going to be this way. So of course, by law of indices, we can evaluate this by multiplying this and that. When you do that, you should have something like this. because you can bring out minus out, which is common to the both of them. Then inside, you're going to have s plus a that, and bring out t, which is common to the both of them. Now, recalling the same way we did for this case, the same way we did for this case. Now, the same way we did for this case. So you can see we're not going to have minus 1 all over s plus a exponential minus this, that. Remember, it's now looking like this. The only difference is because we have a, and which came as a result of what? This exponent here. So you can see that this and this, they are the same. So we still have minus 1 over x, which is minus 1 over x. Then in our own case, because it is not just x, we have a, it is shifted by a. Then we have a here. Then you have the same thing here. Then you have the same thing there. You can see, then we go the same way we did by substituting. When we substitute, of course, we know that we're going to be having the upper limit, which is this, representing t with infinity. When you do that, you're going to have that all of these function will become 0. And then replacing with 0, you're going to have all this function becomes 1. When you multiply everything here by 0, this will be minus exponential minus 0, of course, which is going to be 1. And that's why you have 1 here. So this is what you're going to have. Remember how this plus sign came here, because it is supposed to be minus this raised to power infinity minus, because you're going to minus the lower limit. So say minus, minus. So is that minus, minus that brought about plus this? Now also this raised to power this, 0, replacing t with 0. And that's how we have 1. So at the end of the day, when you run this and do your mathematics, this becomes 0, and you're going to have this. Now let's look at another function also. Very important function in mathematics, the impulse function. It is actually used to represent impulsive functions, used to represent impulse, something that appears at a definite time and remains 0 at all other times, remains 0 all other times. So now let's look at this. When we look at this, then we see that this function, derivative or impulse function, now we're also integrating it. We want to look for its Laplace transform. So this is our f of t. So we bring it in here and we integrate. Now we've told you initially, this is an impulse function. An impulse function is 0 every other point. It only exists at the point where t is 0. Now from this here, where what we have here is that this function only exists at t is what? 0. Of course, we didn't create some delay. If we have considered this function like a delay function, we're going to have Dirac into t minus 1 in bracket, or t minus 2 in bracket, or t minus 3. So in that case, we say it's a function that exists after 1 second, after 2 seconds, or after 3 seconds. But in this case, it's a function that exists only at what? 0 seconds. So it is 0 every other place. So the only place where it has value is only at point t is what? 0. So mind you that we're integrating over 0 to infinity. So of course, we don't need to consider any other part, because we know definitely to infinity, every other point outside 0 is 0. So the only point that exists for it is actually what? 0. So, and that's why we just come here. There is no need carrying out integration. This is the way this function behaves. Subsequently, as you move in mathematics, you get to understand it better. But this function does not have any other value. So if, for instance, we say this is 5 Dirac t, yes, if we say 5 Dirac t, it then means this function has a magnitude of what? 5. Of course. So instead of having 1 here, we're going to be having 5 times what? 1. If we have 6 Dirac, we're going to have 6 times what? 1. So, of course, this is a function that does not exist any other place. So, it only exists for this function. It exists only at what? T is 0. You can read about the Dirac function. Then, another very important function we're going to be looking at is a sine function. Now we can see the sine function. We have to look for the Laplace transform of the sine function. So this is our f of t. So we'll bring it into the formula for Laplace transform so that we can carry out our integration. So you can see there are shorter ways by which we deal with problems of this kind. Now, one way is to convert this sine omega t into an exponential function. And one way to do that is to remember the Euler's equation, where we have that recall that exponential j omega t. I know from your trigonometry, you've not forgotten your one. You're back to your mathematics again. You have that exponential j omega t is equal to cos omega t plus j sine omega t. You agree with that? You also agree that exponential minus j omega t is equal to cos omega t minus j sine omega t. Now, if you agree with that, let us also consider this situation. What if we say this minus that? That is to say, this minus this. So if we do that, this minus this, we're going to have this minus this minus this. You see, this will go. This minus this, you are going to see we're going to have 2 sine j omega because they are going to add. Minus minus will become plus and they will add and you have this. Hence, we can say sine omega t will be equal to this divided by 2. That's the start. This divided by what? 2j. Oh, we made a mistake here. We made a mistake here. Now, listen. Okay, let's look at it. Let's look at it. Let's see if we can correct that. Let's correct that now so that you don't go with that error. Let's correct that. So, okay, j omega. This shouldn't be here. Then you should have this here. Then you should have j here. Okay, good, 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 good. Yes, we should have our j here. Fine, good. I think we are good to go. Okay, so you should have 2j sine omega t. Hence, sine omega t will be equal to, of course, we have said that, this minus that, all over 2j. So substituting, yes, when we substitute for sine omega t, yes, which is that, we're going to be having that. Okay, there's an error. Let's take away this equality sign here. Let's take away that equality sign there. It shouldn't be there. Let's look at it. Yes, that equality sign shouldn't be there. Okay. Good. That equality sign shouldn't be there. Okay. Okay, let's make progress. Okay. So you have that, this is substituting that, then you have this, and that. Then instead of sine omega t, we are now going to be introducing this, then exponential minus s of t. Of course, you know, we are not going to go through all of this again, trying to deal with them. Now recall that when we had uh, this, where is that function? Minus exponential e raised power minus at. Please remember that at the end of the day, we got 1 over x plus a. So in this case, let's look at what we are going to be having. Now, in that case, you see we're having 2 functions here, this j omega, and one of them is negative. So we are going to expand it with this. So when you expand, we can bring out this outside, and that's why we have 1 over 2j. Then when you bring that in, you're going to be having, okay, okay. So we have an issue here. Let us just deal with this. Let's take away that. Good. Yes, let's look at take away that. Good. So that we can have okay. Now you can see that. So when this goes in, of course, when we take this in, of course, you can see when we have, let's look at it. Let's look at it together. So of course, you have one of them will be of this form. Exponent, this exponent minus s of t. When you bring it, you deal with this. You're going to have minus. You can see minus j plus j omega x plus j omega t. Then when you bring this to deal with this, of course, you can see. Now look at why we have this. Now you can see we brought out minus into x minus j. Now, if you expand this, of course, you know this should be minus x plus j omega t, which is actually this. This is plus j omega t. So you can see we have expanded that. So we're integrating with respect to what? The t. And when we do our integration, you still remember what we did here. So you can see what that gave to us. And let us see. Let us see what it gave to us. So you can see now this will be equal to 1 all over, which is this, that. So you can see 1 all over s minus j omega. So now look at this. This is x plus a because we are dealing with what? Minus into x plus a. Now, in a case when we are dealing with what? Minus into x minus that. So you can see why our own was giving us minus x instead of plus, we're having minus. Then in this case where we're having this, you can see this is similar to that. So you can see at the end of the day, we're having 1 all over s plus j omega. So now when you expand this, of course, how do you expand? By taking LCM. Remember that this j, by implication in mathematics, this means root of minus 1. I hope you still remember that that j means root of minus 1 in your complex mathematics. That is what it means, root of minus 1. So when you deal with that, of course, what are you going to have? When you deal with that, what are you going to have? When you deal with that, what are you going to have? Of course, you're going to have at the end of the s squared plus omega squared, and you're going to have this going to come up. So you go and carry out, do your calculation, expand this, of course, and you are going to see what you have. Very interesting. It's just work for you. So sit down, do this expansion. Like I said, this means root minus 1. This also means root minus 1. So when you take the LCM of these two, this will be multiplying this. You have this will come up here. This will go up here. Then you are going to do your subtraction. At the end of the day, you are going to have, we're going to have just omega remaining because one of the omegas, well, when you do it, you see that the omega at the top will have to cancel the omega at the bottom. Good. And when that is taken care of, okay, please let us deal with this stuff that is giving us trouble here. Okay, so when you have that, then of course you're going to have the j omega at the top. It will be canceling the j omega at the bottom of the work. And when that is done, good, you are good to go. So let us look at another one. Okay, before the properties. So okay, let us look at this. So you can see, just go and expand that, and you're going to see at the end of the day, you're going to have this. So I believe this is well understood. So let's move now. This is just the basics of the transform, but I want you to go and expand on what we have done, and you get to appreciate it. So now this is an assignment for you. We are to find the Laplace transform of these functions. You have a function tu of t, Good. So this is a ramp function. Now this is an exponential function. You know, in our own, we considered exponential minus 80. Now we are considering exponential 80 u of t. Now, yeah, in our case, we consider sine. Now here we are considering cos omega t u of t. So I believe if you try this and you're able to do them, wow, so beautiful. I know what this is going to give to you. I know this is going to give you 1 all over s squared. That's what you're going to have here. And in this case, now let's look at the other one. What did we have? This. Good. So you see, your guess is as right as my 1 all over x minus a. I believe you're going to enjoy it. X instead of x, you know, x plus a, like you have here, you're going to have x minus a. So you try it. Here, cos omega t u of t. Woo, what is that going to give to you? Well, I bet you try it. At the end of the day, you're going to be having something like x all over x squared plus omega squared. X all over x squared plus omega squared. That's quite interesting. So you just go and give it a try and let's see what you are going to have at the end of the day. So can we move in now into the properties of Laplace transform? What are these properties? Now, very simple. We have the first property here is scaling. Now, the scaling property. Now, what do we mean here? If you have a function, in frequency domain of this form, which is a transform of a time function of this form, then the Laplace transform a of t, when you scale it, that is to say, instead of having f of t, you have f into at. That is a multiplying the t. You're going to have this, the Laplace transform a of t, and it's going to give you in this form. Wow, what does it mean? Then it then means that scaled value, this is a, you're going to be having at the end of the day 1 all over what? A f into what? X all over a. Now you may try to prove that to be sure this is correct. Maybe you can use this function to prove it, but then we say if you have this time scale understanding of the time scaling, if you don't want to solve it by proving all through, you can just write out your function like this. Already we know the Laplace transform of a sine omega t. The Laplace transform of sine omega t we have found to be what? Omega all over what? S squared plus what? Omega squared. So now it is telling you that you are going to divide all the frequency term by 2. So first and foremost, divide the entire function, which is the Laplace transform of the function, which is this, divided by 2, which is what one here, multiplied by 1 over 2. Then divide the frequency terms by what? 2. And when you do that, if you work out this is what you should have at the end of the day. Okay, let us make this look quite proper. Can we make it look a little proper? Okay, let us see. Let me look at this. Okay, can we make it look this way? Okay, good. So can we make that remove this double sign? Good, so that we can have this look in this way. That's fine. Okay, and let us bold this. Okay, so we have looked at what we call the time scaling. We have looked at the time scale. So now let us look at time shifting. Now, what if we look at the time shifting property? This is also another property of Laplace transform. So we said if f of x is a Laplace transform of f of t, then when we time shift. Now, what we mean by time shifting is that if we have the function f of t and we shift it by a constant a, you can see that at the end of the day, that is the Laplace transform of the function. Instead of function of t, we have shifted it by a. Good. You see, instead of t, we have shifted it by a. Good. Where a is far, far, far greater than 0, we are going to have this as a function. So what do we mean? Just the same way we did if we have sine omega t, we have that as sine omega t. Then instead of omega t, we are now having omega into t minus a. That is, we have shifted it by a, and we have also shifted that by a. That at the end of the day, we are going to have the Laplace transform of sine omega t, and we're going to have it multiplied by what? An exponential function of this nature. An exponential function in x of this nature. So you can see the exponential function here. So this is the effect of time shifting a function by what? A. And you can see this is what we have at the end of the day. We have the Laplace transform of the function. We have it being multiplied by what? A frequency shift of this nature. Okay, we have it multiplied by what? An exponential function in x of this form. I hope you still remember that this is the Laplace transform of sine omega t. So the reason why this is coming is because of what? This shift in A, this shift in A. So look at the effect this created on the sine function. So it created this as an effect, you know, to the shift that we have here. Okay, let's look at other properties. Now we look at frequency shift. Now, if f of x is the Laplace transform of f of t, then the Laplace transform of this, that will be equal to what? This, and which will be equal to that. Now, what are we trying to say? Now, if we have an exponent multiplying a function in time domain, now, this is the function in time domain. We have that an exponential of this form is multiplying it. Then this, which is the Laplace transform, we have that at the end of the day, we are going to have in the frequency domain that the frequency will be shifted by positive A. Now, look at it. Here is negative A. Here is what? Positive A. That is, this is an example here. If we have sine omega t, of course, being multiplied by what? An exponential function of this form. What effect is it going to have on this, the Laplace transform of this? So when we look for the Laplace transform, we see what happened. Of course, while the Laplace transform of this we have proved from our first example is equal to omega all over s squared plus omega squared. So we have that because of this function, it has introduced a positive shift in the frequency component by what? A function of what? A. So this is for the frequency shift. So we have another one, which is what? The time differentiation. The time differentiation. Now, what is it about this time differentiation? Now, we know that Laplace transform also can be used to solve differential equations. So when we have a differential equation of n order, now this is a differential equation of n order, we'll have it in this form. This will give you something of this nature. S of n, f of x. I hope you can see that. F of x. Then we go down, and we have x raised to power n minus 1, f of o, x raised to power n minus 2, f1 of o, and continuously down to that form. Now we take, for example, look at a second order differential equation. Just like we have this dn of x, we're going to be having x here. Now with respect to this, so what we have there is 2f of x. So we're going to have minus. Then this will be what? N minus 1, which is 2 minus 1, and therefore you're going to have x, then f of o. Then whereas here will now be what? What are you going to have here? Here you're going to be having x raised to power what? 2 minus 2. Of course, s raised to power 2 minus 2 will be s raised to power 0, which will be what? 1. And here is going to have what? F, which is this function. Okay, let us correct this here. Yeah, here you're supposed to have, this should be raised to power 1. You're going to be having that function raised to power 1. So let us just introduce that here so that you have it here. Good. So you're going to have this function as raised to power 1. That's fine. So you're going to have this raised power. So it's the same. When you have, what if this is 1? What if this is a third order differential equation, fourth order, as the case may be. So this is the way to handle it. Now, if it's a third order, of course, you expect that this will start with S of 3. Then the next one will be S of 2. Then S of 1, then to the end. So depending the case, if it is what, a fourth order, this is going to be F4, and you're going to start with S of 4, S of 3, S of 2, S of 1, then S of 0, of course, which should be 1. Then we have time integration, which is another property very important. Now, if we're looking at time integration, you're going to be having Laplace transform of what? This f of t d of t. Now, if this f of t is an integration, you can see Laplace transform of an integral. If this is the Laplace transform of an integral, you're going to be having 1 over x over f of x. That is what this is telling us. Just like you have the Laplace transform of a differential here, this is a Laplace transform of an integral function. This is what is going to be 1 over x, f of x. Now, just like we have here, the Laplace transform of 1 over c integral t all over o I d of t. So this is the Laplace function transform of an integral, which is multiplied by 1 over c. We give you the same thing, 1 over what? Sc. Of course, like we have here, 1 over x. Now, this c is coming because of this c. Then what? I of x, which is this. Now, from time domain to what? Frequency domain, just like you have this from time domain to frequency domain. Okay, now this is frequency differentiation. Now, of course, we have frequency differentiation. If we have the Laplace of t and f of t, u of t. I know you notice in the assignments you were given to try out, you have a function that looks like this, t. Now, but your own, we don't have it raised to anything. But when you have only t here, it means t raised to power 1. So in this case, we have t raised to power n. So if you have a function of this t raised to power n, f of t, u of t, of course, if you have it and you want to integrate it, it's going to give you this way, minus 1 into that, and raised to power n, d of n, f of x, ds of n, and that's, and that's what you get. So let's look at an example under this with the Laplace transform of t exponential minus a of t, u of t. So when you have this, for instance, imagine if there is no this, we'll just consider this to be 1. But in this case, we'll have it. So what is it going to give to us? Look at what? The Laplace transform, what is it going to be? Good. It's going to be bracket here, minus 1 into, this is raised to power n. So what is the n here? What is our n here? Our n here, of course, should be what? 1 d dx of what? 1 over x minus a, which is the Laplace transform of this function. Just like we have here f of t, this will be the Laplace differential of the Laplace transform of what? F of x. And the order of the differential would be with respect to the power of t. Now, the order of differentiation here is what? With respect to the power of t here is 1. So we're just going to differentiate this once. So when you do this, of course, with what you know about differentiation, of course, you square down, take one side. I still know you remember how to deal with differentiation, where you have, when you deal with that, at the end of the day, you are going to come down to this. Then time periodicity. Of course, when you have a function of time in t, a function of f of t, the Laplace transform of that function will give you f of s will be equal to f of x. That is, you take the period of the function. This t here represents the period for a periodic function. You understand what we mean by periodic function? A function that, repeats itself after a given period. Where this represents the period of the function, this is the Laplace transform of the function. So if it's a sine function, then you should have the Laplace transform of the sine function. If it's a cosine function, you should have the Laplace transform of the cosine function. Depending on what the function is, you find its Laplace transform, then divide it by 1 all over what? Exponential minus t of x, where t here we say represents the period of the function. A better example will help to trace this. I say you refer to the recommended textbooks for this course so that you can have in-depth understanding. We may not be able to cover everything regarding Laplace here, but I can assure you it's a very interesting topic. Just do the little work you can do to study deeply so that you may get deeper understanding. Okay, another property here we want to look at is the initial and final values. Of course, with the Laplace transform, we can determine the initial and final value of a function. Now, if we have a function f of t, we can find its initial value, we can find its final value. Now, the initial and final value properties allows us to find the initial value f of o and final value f of infinity of f of t directly from its Laplace transform f of x. Of course, so you can see here the initial value f of o is equal to the limit. We take the limit as s tends to infinity for s f of x. Remember, s tends to infinity. If we are looking at it from what? The frequency domain. To find the final value, we consider the limit of this function as s tends to infinity. Example, we have given that this function of that. Remember what we said, this is what? A frequency shifted problem. You can see we have a function being multiplied by what? Exponential minus s of t. Cos 10t being multiplied by this. Of course, solution. Now, when we have f of x is equal to what? The Laplace transform of this. We want to get it first in frequency domain. So in frequency domain, of course, the Laplace transform of cos 10t should give you x all over what? S squared plus what? 10 squared. Now, because of this shift here, because of this multiplication here, that's why we're having a shift in the frequency, which has shifted it to what? Minus what? 2. And this side also, the frequency by minus 2. Anyway, I believe by when you have solved some of the assignments we gave, you would come to a full understanding of this. So let's move forward. Okay, so applying the initial value theory, we have said that initial value of this, mind you that what are we looking at? We are giving this, we are to obtain its initial value. So first and foremost, what we did was to convert this to what? The frequency domain, because it was given to us in time domain. So we want to convert it to frequency domain, and that is what it will give to us in frequency domain. So now we apply the initial value theory. The initial value theory, which is f of o, says is equal to this lim. Take the limit as s tends to infinity. While you multiply this by s, you multiply the frequency function by s. So when we multiply the frequency function, so you can see that bring in s here and multiply. So when you multiply that, you're going to be having s squared plus what? 2x all over x squared plus 4x plus what? 104. Of course, when you come down here, you should be having what again? So what we did here was to divide the up and downside of this expression, this equation, by what? By the highest power, which is s squared. That is what we did. We divided the numerator and the denominator by what? By s squared. So when you carry out that division, now what was the purpose of doing that? Yes, the purpose of doing that is to make this function, bring it to a normal fraction where, for instance, we'll be able, because if we don't do that, the implication, if we don't do that, if you just substitute s into infinity here, you see everything here will go. Of course, you are going to be having infinity divided by what? Infinity. So by doing this, we'll be able to deal with this infinity very well. So when we do that, you can see at the end of the day, we're going to be having this, and this. So at the end of the day, we can afford to substitute s is infinity. If we put s is infinity, you're going to have 2 all over infinity, which is 0. You're going to be having this all over infinity. Anything divided by infinity, of course, you know how large infinity is. Of course, that thing, whatever you're going to get is equivalent to 0. So that's why at the end of the day, when you do this, this becomes 0, this becomes 0, this becomes 0. You're going to be having 1 over 1. So, and then you're going to have 1. So, which is to say that the initial value for this function here, its initial value is actually what? 1. That is to say, it starts only from 1. Okay, having established that, let us look at the final value problem. Now, let us look at this. We want to determine the final value. Now, the final value problem, which is f into infinity, remember s into infinity, by here we mean final value, is equal to what? Leave f of x, then we substitute as s tends to 0. Look at for initial value, s tends to infinity. For final value, s tends to 0. Please do not forget, now, when we say final value, in the time domain, it means infinity. But in the frequency domain, it means 0. When we say initial value, in the time domain, it means 0. In the frequency domain, it means infinity. Now, how best can you understand this? Remember that time is the opposite of what? Frequency. That is, time is equal to 1 over f, or f is equal to 1 over t. I hope that refreshes your mind now. So when you have this f over infinity, which is what? The final value theorem. Now, and we're going to test for it in frequency domain by substituting for the frequency when by looking for the value of this as s tends to what? Tends to 0. That will give us the final value. So example, given a function of this form, good, determine its final value. And solution, then we have f of x is equal to that. Now, when we take the Laplace transform of this function, this will be equal to this. Now, of course, you recall that you go and work this out, and you see that, of course, we told you this is a frequency shift problem because it's going to cause a shift in this side, 5t. Now, the Laplace transform of sine 5t should be 5 all over s squared plus 5 squared. So because of this man here, it is now shifting this to give you what? 5 all over what? Now the frequency has been shifted by what? By 2. And that's why we have this. So we are just trying to recall your mind so that you can keep these things in mind. So when you have that, so we said, using the final value theorem, now we have substituting when s tends to 0. Then we have that. Of course, you know, we are multiplying the f of x by x. So this is f of x multiplied by x. You're going to have this. At the end of the day, you're going to have 5x all over that. So taking the limit as s tends to infinity, we have now, you substitute for x. This is 0 all over what? 0 divided by what? 5 squared. So now recall that here we don't have any need to start dividing up and down by what? The limit, because it will not create any challenge for us. We will not have to be dividing, because if we allow, in the other case, that is for the initial value theorem, if we are substituted infinity, we will not be able to deal with it, because when you have infinity here, anything dividing infinity, of course, will give you infinity. You also have infinity divided by infinity to also give you infinity, because you and me cannot do any calculation infinity. But in this case, because we are substituting s tends to 0, we are not bothered with trying to divide the top and down, the numerator and the denominator by what? By x. So we just go ahead and substitute x as, we substitute the limits as, substitute x for 0 as the limit tends to 0. So when you do that, at the end of the day, you see this. So that means your final value for this particular function, your final value for this particular function is actually what? 0. Okay. So I believe We've been able to do something here. So look at this for you to try. Find the initial and final values. Okay, we say values. Okay, let me correct this. Initial values. Okay. Okay, good. Yes, find the initial and final values of a function whose Laplace transform is this. So in this case, you see, we have made it easier for you. So you don't have to start trying to convert from time domain to frequency domain. They are all been given to you in frequency domain. But mind you that you can't deal with this. You have to expand this so that you can get the highest factor of, value of x here, the highest power of x. So you need to expand this. In this case, you need to also do the same thing, expand so that you can get the highest value of x if you would want to calculate what? The initial value. So these are the answers. In this case, both are 0. In this case, we have they are 1 and what? And 2. So summary of the properties of Laplace transform. So this is the summary of the property of Laplace transform. We have linearity. You can see that. We have the time shift. We have the time scaling. Remember what we said about time scale, A of t. Can you see that? You remember the time shift, where you have a function shifted in time, is going to give you another function. It's going to give you the Laplace transform multiplied by what? An exponent, of the same AX. When you have frequency differentiation, we did that to show you frequency shift. When you have a function multiplied by that, you can see this is what it gives to you, the Laplace transform shifted by what? By A. Then you have differentiation. When you have that, this is a first order, this is a second order. You recall what we said about them. This is an nth order. This is for integration. We should be 1 over x, s of x. Of course, time convolution, the rest of that. Ooh, so many things for us to look at. So now, we didn't look at time convolution, but as we proceed, I am going to take us also on time convolution so that we'll be able to understand what time convolution is all about. We have time convolution, we have frequency convolution. So we're going to look at just time convolution as we proceed in this class. So thank you so much for listening. I would advise that you try out all the problems that we have listed here. They will help you to understand better. As you solve them, you get to appreciate this topic more. But like I said, there are 2 more videos to watch so as to help build your understanding. If you have questions, please, you can reach me directly via WhatsApp or through your class rep. Thank you so much for listening, and see you some other time, perhaps in our next class.